Hi everyone, in this video we would like to discuss the voltage drop calculation inside our power system. So what is the voltage drop? Voltage drop simply it means that if we have a supply like this one 120 volt AC, this is our input supply voltage, and we have a wire connecting between this supply and our load. So between our supply and our load there is a conductor or a cable. This cable have a specific resistance and specific reactance. So this means that this resistance or this inductance will cause a voltage drop. So if we have an input voltage 120 volt AC, the voltage which reaches our load is 112 volt AC. Why? The difference between 120 and 112 is considered as a voltage drop inside our circuit. So we have a difference of 8 volt. This 8 volt is a voltage drop due to the presence of our cable. As you remember that the voltage drop in any circuit from the circuits, if you don't understand what is the electric circuits or anything about electric circuits, you can check my own course for electric circuits. So the voltage drop across any conductor is equal to the current multiplied by Z. Z is the impedance of our conductor, or Z equal to the square root of R square, the resistance square, plus XC square. XC, XL, not XC, XL, L square is the reactance of due to the presence of inductance of the conductor. So the voltage drop happened due to the presence of Z of the wire. So in our power system we would like to calculate the voltage drop. So in our course we discussed how to calculate using the ETAB program. In this video we would like to discuss how to do this but using the manual calculations. So before we start going to the calculation part, we would like to understand what is the effect of having a voltage drop inside our system. Number one, for electric motors, remember that from our course for electric machines, that the torque is directly proportional to the square of the supply voltage. So as you see that the supply was 120 volt. But the voltage reached to the load is 112. So we have here the torque is reduced by square of the value due to the presence of voltage drop. So the reduction in the voltage will cause the starting torque to be decreased, the torque of the motor to be decreased, maximum torque will be decreased. All of this will affect our motor. Now another thing that for lamps the presence of the voltage drop will cause the light intensity or the beam becomes weaker. Also in the electronic appliances are very sensitive to the voltage variation, so the voltage drop will affect them very high. Now as an example, what is the value of the accepted voltage drop? So if we have a low voltage system taking its power from the public utility, okay, or the public low voltage distribution system, and if we have a low voltage installation but it is supplied from a private low voltage supply. So if it was from a low voltage distribution system, or it was from a low voltage private supply, my own supply, a generator for example, then if we are using it for lighting, then the accepted value is, if you are taking from the public utility, then the accepted value is 3%. If we have a private low voltage supply, then the accepted value is 6%. Now if we are talking about a general use or a general usage in our system, then if we are taking from public utility, then we will have a 5% voltage drop only. But if we have from our private supply, then it is 8%. So generally when we are talking about our system, if we have the system 5%, we usually take the voltage drop as a 5% from our supply. Okay, we usually, when we are talking about ETAP, for example, we would like to make the voltage drop less than 5%. Now, as an example, what is the exceptions to this IEC rule? The previous values are according to the IEC 3064-5-52 standard. So what is the exceptions to this rule? Number one, a greater voltage drop may be accepted for: number one, electric motors during the starting period. For other electrical equipment having high inrush current, such as the transformers have high inrush current. So this can cause higher voltage drop, but it can be accepted. Why? Because it is for a very small time. But provided that in both cases that the voltage variation should remain in the limits specified in the relevant equipment standard. So what does it mean? It means that our equipment should have a specific under voltage and specific over voltage. Okay, so we have a specific limit according to the data sheet or according to our equipment. So this limit should not be exceeded, okay, according to the equipment itself. Now the following temporary conditions are excluded from the voltage drop restrictions. So what is the example of this? Number one, if we have a voltage transient, if there is an increase or over voltage or under voltage due to switching. As an example, if we are adding loads, then the voltage will be reduced for a specific time. Or if we are removing loads, so the voltage will express over voltage. All of this are considered as a voltage transients, which are just for a few moments or a very small time. So these values are accepted from our IEC standard. Also the voltage variation due to the abnormal operation, okay, due to any abnormal conditions in our power system. Now, how to calculate the voltage drop in our system? Simply, the voltage drop of the cable is calculated by obtaining a value called the voltage drop percentage or voltage drop from our catalog. This is found from the cable itself. You will find that the cable voltage drop is equal to millivolt per ampere per meter. Okay, so we can take the type of the cable, then go to our catalog and get this value for the voltage drop, as we will see now. The percentage of the voltage drop, which cannot exceed 5%, is equal to the actual value, the actual voltage drop value in volt, over the base voltage. For example, if we are talking about a single phase system, then it will be, for my own country, 220 volt as an example. If it is a 3-phase system, then it will be the line to line voltage, which is 180 volt for my own country. Multiplied by 100 will give us a certain percentage. This percentage representing the voltage drop inside our system, which cannot exceed 5% if we are taking power from our public utility. Now let's have an example. If we have a supply voltage like this one, frequency equal 50 Hz, voltage equal 400 volt, and we have here a motor, 3-phase motor of a 75 horsepower. And we have a cable connecting between this supply and this motor. Remember that the 5% is from the supply to the load. Okay, so if we have a bus bar having other loads, then we should have the volt or calculate the voltage drop from the supply itself to the load. Okay, so if we have another cable, then we will take it in consideration. Now, as an example, if we have a bus bar like this, and we have another load here, another one here, then the voltage drop, we have here our supply and here a cable and another cable here. So we have to calculate the voltage drop here plus the voltage drop here and add them together to get the total voltage drop, which should not exceed 5%. So the voltage drop is from the supply to our load. Okay, now we will have a simple example. If we have a supply and a load, and between them this cable, which is 3 multiplied by 70 plus 1 multiplied by 35, okay, 3 phase plus the neutral, 3 phase of a 70 millimeter square and the neutral 35 millimeter square. The conductor type is copper, and the insulation PVC, and the sheath is also PVC. The length of this cable is 120 meter. So what we are going to do first, we have a cable of 3 multiplied by 70 plus 1 multiplied by 35. So we should go to the catalog and get the voltage drop of this cable. So let's go to the catalog. Now as an example, we have this catalog for LCD cables. We would like to get the value of the voltage drop. So we'll go to the catalog or through the catalog and search for the voltage drop. Okay, so we have here a voltage drop. Let's zoom in. So voltage drop for a single core low voltage. Here we have a 3 phase or a multi-core, 3 core or multi-core plus neutral. So let's search for this one, multi-core. Okay, so this one is the multi-core. Now the multi-core, we have here a PVC insulation and PVC sheath, cross-linked polyethylene, and we have here another one. But what is the difference between them? Okay, let's see what is the difference. You will find that this one is copper conductor and this one is aluminum conductor. So we said that we have a copper conductor of a 35. Let's get back. We have a value of 70. Okay, 70. So let's get back. Okay, so we have a 70, cross section area 70. So for PVC insulation, PVC sheath, voltage drop is equal to 0.524. So the voltage drop value from the catalog 0.524. So now simply you have got to the you went to the part for the catalog of the voltage drop, and you take the cross section area of 70, and you know it is copper, PVC. So you will find that the voltage drop is 0.524 millivolt per ampere per meter. You will find that this value is written inside the catalog as you have seen. Now in order to convert this voltage drop to the actual value, then we will multiply 0.524 by 10 power negative 3 to convert the millivolt to volt. Okay, so this part representing the voltage. Okay, now this is the voltage, but it is per ampere per meter. So in order to convert it to volt only, we will multiply by the current and multiply by the length. So length is given as 120 meter. And this is a 3-phase system. Now the I rated, how to calculate the I rated? The I rated is the current which absorbed by our load, which is 75 horsepower. So how to calculate this? Remember that from our course we said that the current rated in case of a 3-phase system is equal to 1.5 multiplied by kilovolt ampere, or 1.5 multiplied by horsepower. Okay, we have said that inside our course that the kilovolt ampere is nearly equal to the horsepower. So 1.5 multiplied by 75 will give us 112.5 ampere. 75 is the horsepower. Now if you don't understand where we got the 1.5, let's remind you. Now remember that the kilovolt ampere, we said that the 1 horsepower is equal to how many watt? Is equal to 746 wattage. Okay, so each 1 horsepower equal to this value of wattage. Now if I would like to convert the power or the active power, which is 746 watt, to the value of the kilovolt ampere, so we divide by power factor. So the power factor assumed in our system is 0.8. So divided by 0.8. you will find that it's equal 932.5, which is nearly equal to 1, okay, or unity. So we say that each horsepower is nearly equal to 1 kilovolt ampere. So that is the first thing. Second thing, we would like to get the current. Remember that the current is equal to S. Okay, let's write it. Now remember that the current is equal to the current from our system. Since this is a star connected motor, then the current is equal to S over 3 multiplied by V phase, okay, or root 3 multiplied by V phase, or root 3 multiplied by V line to line, okay, both of them are correct. Now if we have our supply here is 400 volt or 380 volt, the difference is 4 volts drop. So we assume that here the motor reaches is 380 volt as a line to line voltage, of course. So we have 3 multiplied by V phase. Now this V phase will be equal to 220 volt, okay, V phase, but the line is 380 volt. Now S here is given as kilovolt ampere. So in order to replace this S, which is in volt ampere, to S in kilovolt ampere, then we will have to multiply here by 10 power 3. Okay, so we can put 75 kilovolt ampere multiplied by 10 power 3, okay, to give us the voltage ampere. So 10 power 3 over 3 multiplied by 220 will give us nearly 1.5, okay, which is this value. So where did we obtain this value? Remember that the current is equal to the apparent power S over 3 multiplied by V phase, or root 3 multiplied by V line to line. So V phase is 220, or line to line 380 volt. Okay, remember that 400 is the supply and the voltage reaching to the motor is 380 volt. So the division of 10 power 3 over 3 multiplied by 220 give us 1.5, which is this factor. Now we have our current and we have our length, which is 120 meter, and we have the voltage drop value 0.524 multiplied by 10 power 3. So we can get the voltage drop is 7.074 volt. Okay, this is the voltage drop in our system here. Now, in order to get the value as a percent, since it is a 3-phase load, then the percentage voltage drop is equal to 7.074 over the 380 volt, which is the line-to-line voltage, multiplied by 100. Give us 1.861%. Okay, this percentage representing the voltage drop in our system here, from this supply to here. Okay, so you will find that 380 volt here, we assumed it is the voltage which reaches the motor. Okay, if you take 400, then it will give us a lower voltage drop. Now how we can solve the problem of the voltage drop? Remember that the resistance of the conductor or the cable is equal to rho, or the resistivity, multiplied by the length over the area. So number one, we can increase the cross-sectional area. If we increase the cross-sectional area of the cable, then the resistance will be lower, therefore the voltage drop will be lower. This is the first solution which we always do. Second solution, increasing number of parallel cables. Increasing number of parallel cables means that the total equivalent resistance will be reduced. So if we have one cable like this of a resistance R, and we added another cable in parallel with another resistance called R, so the summation of the two resistance will give us R over 2. We have a 2 parallel resistors. The third solution is the reduction of the distance. So we can reduce the distance from the supply to the load. If we can, this will cause the total resistance to be reduced and the inductance to be reduced, which in the end will cause the total voltage drop to be reduced. But usually the two solutions are increasing the cross-sectional area. Then if we exceed or reach the maximum cross-sectional area, then we will choose two cables of lower cross-sectional area, which in the end will reduce the total resistance, which will reduce the voltage drop. The last factor is the power factor correction. By adding capacitor banks, we can supply Q or reactive power to our system, so it will reduce the X or the reactance, of course, or the effect of the inductance, and in the end will improve our voltage profile. So in this video we discussed the voltage drop, its effects, how to calculate it, and the solution of the voltage drop.